There are two common interpretations that we will use for the area under the normal curve. So suppose that a random variable x is normally distributed with a mean of mu and a standard deviation of sigma. The area under the normal curve for any interval of values of the random variable x represents either 1. The proportion of the population with the characteristic described by the interval of values, or 2. The probability that a randomly selected individual from the population will have the characteristic described by the interval of values. So these are the interpretations that we're going to be using when we find the area underneath the normal probability curve. So we're either going to think of that area as a probability, or we're going to think of that area as the proportion of the population that has the given characteristics. Let's look at an example. The heights of 10-year-old males are normally distributed with a mean of 55.9 inches and a standard deviation of 5.7 inches. A, we're supposed to draw a normal curve with the parameters labeled. B, we're supposed to shade the region that represents the proportion of 10-year-old males who are less than 46.5 inches tall. And C, suppose the area underneath the normal curve to the left of 46.5 inches is 0.0496. We want to provide two interpretations of this result. So, if we draw our normal curve, we know the mean is 55.9 and the standard deviation is 5.7. So if I draw my normal curve, here's my variable x, the mean is 55.9. And if I take 55.9 and add the 5.7, the standard deviation, let's see, that's going to be 61.6. So at 61.6, that will be where this inflection point occurs. And if I take 55.9 minus 5.7, that will be 50.2. So over here at 50.2 is where this inflection point will occur. So here's our answer to part A. We've drawn a normal curve with our parameters labeled for this particular situation. Now part B, we're supposed to shade the region that represents the proportion of 10-year-old males who are less than 46.5 inches tall. So compared to our 55.9 and our 50.2, 46.5 would be over here to the left, so 46.5 would be over here, okay? And so we're supposed to shade the region that represents the proportion of 10-year-olds who are less than 46.5, so that would be this area over here to the left. So this area is representing the proportion of 10-year-olds who are less than 46.5 inches tall. Okay, so this is our answer to part B. Part C, suppose that the area to the left of this 46.5 is 0.0496. So this is 0.0496. We're supposed to provide two interpretations of that area being 0.0496. Well, our two interpretations are, it could be the proportion of the population that has the characteristic, or it could be the probability. So the first one. So this would mean that 4.96% of 10-year-old males are less than 46.5 inches tall. So out of all 10-year-old males, about 4.96% of them are less than 46.5 inches tall. That's one interpretation. Our other interpretation, if we were to randomly select one 10-year-old male, then the probability that that 10-year-old male would be less than 46.5 inches tall would be 0.0496. Okay? So the probability that a randomly selected 10-year-old male the probability that a randomly selected 10-year-old male is less than 46.5 inches tall would be 0.0496. So we have our two interpretations. 4.96% of the population of 10-year-old males is less than 46.5 inches tall, or if we randomly select one 10-year-old male, the probability that that male is less than 46.5 inches tall is 0.0496.